You are watching the 3.6 lesson video on applications of linear functions, day 1. So there's lots of examples. Let's just get started. So number 1 says if Jenny can run 5 meters in 2 seconds. So Jenny can run 5 meters every 2 seconds. Then which of the following gives her distance, d, she can run over a span of t seconds going at that same constant rate? Well, if you look at all of the answer choices, we know that d is going to equal something. And since she can run 5 meters in 2 seconds, we're going to multiply that by the time. Now, we need to think because, well, actually, we could narrow our answer choice down immediately to answer choice 4, but let's talk about why there is no y-intercept. So where would she begin? Well, if she didn't run at all, would she have traveled any distance? And the answer would be no. So technically, this number here is 0. We would start at the origin. And this would be our slope. We would go up 5, then to the right 2. Okay, moving on to number 2. Erica is driving at a constant rate and she travels 60 miles per hour. So that just means 60 miles every 1 hour. So 60 miles every 1 hour. It says to graph the situation. So right away we know that if she doesn't travel any time, she doesn't travel any miles. So 0, 0 would be on the graph. Pay close attention to your scale. It's given to us right here. So if she travels for 1 hour, that's the same thing as 60 miles. So 20, 40, 60, 80, 100. Each one of these lines is worth 20. So 20, 40, 60. Okay? And if she does this again, the second hour would mean that she would travel another 60 miles. So 2 miles, 20, 40, another 60, and the same thing. 3 hours, 20, 40, 60. I'm going to use a line to graph this relationship because we can see it's linear, and I'll also put an arrow on the end because this can continue for however many hours she travels. Now, part B says write an equation that models the relationship between the distance and the time. Well, we know that the distance, we could call that d, or d of t, because t is really our x here, would equal, well, we know that a line is typically in the form y equals mx plus b. So what is my slope? Well, my slope was rise, I went up 60 over run. So 60 over 1, which is really just the same thing as 60, times my x plus my y-intercept, which would just be 0. Okay, moving on to 3. Amanda is walking away from a light pole, and it's a rate of 4 feet every second. So 4 feet every second, every 1 second. And if she starts at a distance of 6 feet from the light pole, this is different than questions 1 and 2 because she already has a head start that's constantly going to be 6. Which of the following will give her distance, d, from the light pole after walking for t seconds? Well, right away we can see in all of our answer choices, it's d equals. So d is going to equal 4 feet per second, which would be just 4 over 1, which is 4, times the time that she travels. But remember, it said that she started at a distance of 6 feet away, so she had a head start. So we're going to add 6 onto the rate at which she's traveling. So this would be what? Answer choice 1. In question 4, a housekeeper is charging $15 per hour, so $15 per 1 hour to clean a house. in addition to a flat fee of $20 for the initial house visit. So that means as soon as a housekeeper comes to the house, doesn't even start working, he or she will make $20. That's the initial amount. Since we're graphing this, we know that every hour this is going to increase by $15. But I looked at my scale and it looks like I'm going up by tens, which having the 15 there isn't so great. So I could do a couple things. I could have points in between my lines, or I can think of another equivalent way to write this. So $15 an hour would really mean, well, let's think about 2 hours. How much would she make in 2 hours? Well, we would just double it. So $30 in 2 hours. So every 2 hours, she'll make $30 more. So 10, 20, 30 per 2 hours. 10, 20, 30 per 2 hours. Connecting our points together and showing the arrow at the end saying that this relationship will continue forever and ever until she stops working or he stops working. Now B says write an equation that models this relationship. They gave us some information, which is great. Since it's a line, we can use y equals mx plus b. But my y here is actually my a. So a is going to equal my slope, which is my rise over run, which was 30 over 2 or 15 over 1. All would equal just plain old 15, because 30 divided by 2 is 15. 15 divided by 1 is 15. My x is my number of hours, so that would be 15h, and we have to pay attention to our y-intercept here, which is 20, the starting value that is being charged. Now that we have spent some time looking at the graphs of functions, let's also make the connection to the table. In number 5, the temperature is falling outside at a steady rate of 4 degrees every hour. If the temperature starts at 68, okay, so the temperature is initially 68 degrees, and then every single hour drops 4 degrees. So 68 minus 4 would be 64. Dropping another 4 would be 60, and so on and so forth. So here's our table filled out. Then B is saying write a linear equation that models this situation. All right, well, it's a linear equation, so right away, y equals, you got it, mx plus b. My y here is f. My slope is down for every 1 hour. So my slope is actually negative 4 over 1, which we could write as negative 4 over 1, or negative 4 divided by 1 is just negative 4. So we're dropping 4 hours, or not 4 hours, we're dropping 4 degrees every hour, which is t. But let's think about where we began. Where did we begin? B. We began at 68 degrees. Some of you might say, hey, it makes more sense to me to write it like 68 is where we start, minus 4 degrees every hour. And to me, potato, potato. I almost like this bottom one better because it shows our starting point and then we're taking it away every single time. All right, now in C, it says, according to your equation, what is the temperature when T is equal to 2.75 hours? All right, well, let's bring down our equation. F is equal to, let's use the new one, 68 minus 4t. And they're saying that t is equal to 2.75. So what can we do with that? Well, t is now 2.75. So let's replace t with 2.75. So this would become 68 minus 4 times the 2.75. So F is equal to 68 minus 4 times 2.75 is 11. So 68 minus 11 is 57 degrees Fahrenheit. And we'll just include our unit because we're talking about a real life example. D says, if this cooling continues at this constant rate, how many hours will it take for the temperature to reach the freezing point of water? Well, what is the freezing point of water? Well, that happens to be 32 degrees Fahrenheit. So now we were not given the hours, we were given the temperature. So let's start with our equation again. F is equal to 68 minus 4T. Our Fahrenheit now, we want to be equal to 32, our temperature. All right, so if we continue going, if we continue to solve this, I can move the 68 to the other side of the equation. So 32, let's just sort. So 32 minus 68 will equal negative 4T. Negative 36 is equal to negative 4T. Divide both sides by negative 4, and we end up getting T equaling 9 hours. So it will take 9 hours for the, what's cooling? Oh, the outside temperature. So the outside temperature will reach 32 degrees, or the freezing point of water, after 9 hours. All right, last question. A clothing store makes a profit of $5 for selling a pair of jeans and $10 for selling a sweatshirt. Okay, if the store wants to make a profit of at least $300 in one day, write in inequality. So we know right now we're going to have to use greater than, less than, greater than or equal to, or less than or equal to signs. That can be used to determine the number of each item. Well, the problem right now is we need to figure out the number of each item, and I don't know either. So to me, this means I need to bring in not one variable, but two. Let's bring in an X and a Y. So what don't we know? We don't know the number of jeans. And we also don't know the number of sweatshirts. Let's read in the problem again. So if a clothing store makes a profit of $5 for selling jeans, to me, that means $5 every pair of jeans, 5x. And, okay, so we're going to be adding $10 per a sweatshirt. And they want to make at least $300. So 300 will go over here. But I need to think. I won't put an equal sign there because they don't want to just earn 300. They're happy with earning 300, but they would also be happy if this here were more than or equal to 300. One thing that I like to think about when I'm writing equations is I know that this whole equation deals with money. Money, money, money. The $5 is money, the $10 is money, and the $300 is also money. Therefore, my equation, we're in good shape with this one. Or I keep calling it an equation, inequality. Moving on to B. Will the store make a profit if they sell 12 pairs of jeans and 23 sweatshirts? Well, looks to me we can just do some nice substituting because the jeans, that's my X, and the sweatshirts are my Y. So 5 times 12 pairs of jeans plus 10 times 23 sweatshirts should be greater than or equal to 300. Okay, take a minute, simplify this. So you can see that I simplified and I found that 290 was bigger than or equal to 300. Oh no, will they make a profit? No. They're $10 short, but still $10 off. Oh, bringing back C. Solve your inequality for Y in terms of X. We've done this before. Let's copy paste down our inequality. And what that means is just get y alone. All right, so sorting. Move the 5x on over. Leave the y term where it is. Okay, so bring the 5x over. So I can either write that as 300 minus 5x or negative 5x plus 300. Doesn't matter to me. Let's do 300 minus 5x. Lastly, I don't want that 10 there. This should all be review. Hopefully you're rocking and rolling without me. Y must be, do I have to turn this sign? Definitely not. I only divided by a positive 10. So y is bigger than or equal to 30 minus, well, 5 divided by 10 is just 1/2, minus half of x. And here is my final answer.